Okay, we're now going to talk about functions. And as I said at the end of the last video, functions are very important in mathematics. And we use functions throughout mathematics and future courses. Sometimes people are a little confused why we have this additional notation for functions. And it really has to do with it makes notations, quite frankly, easier in the end, and it gives us a lot more ability to use tools. And when I say tools, I'm talking about other theorems and properties, things like that. So let's just dive in to look at the definition here. The definition of a function is a little confusing the first time you see it, but it's an important definition. So a function f from the set A to the set B is a relation that assigns to each element x in the set A. Now this is what's important here, exactly 1. So this is very important, exactly 1 element y in the set B. So that's actually our definition of a function right there. So a function, it's a function, we call the function by name, it's like f. Now we can use other things besides f. Common ones to use are like g and h, but you can use s, r, you can use any letter you want to for a function. But the most common ones are f, g, and h. Now the key thing is the set A, and the set, a set is just a collection of objects, but for our course, and for our many math courses, the sets might be just, the numbers that we're thinking of, like all real numbers. So for every real number, we're going to assign another number to it. And then what f usually has is that assignment, that's relation that assigns to each element x. That's usually an equation of some sort. Like for instance, 3x plus 2, that's an equation, and it tells us how to assign every element x to an element y. But the key thing here is that each x gets only assigned to exactly one element y. So we can't have this x going to two different y values. X can only go to one y value. Each value of x can only go to one y value. Okay, so let us go ahead and look at kind of a abstract example of this, as well as then some more concrete ones. Alright, now before we do that, there are two other things that are going to be important to us throughout this course and other courses, and this is the domain. The domain here is the set A is your domain. But I like to think of it as the, I'll put it in quote, allowable x values. Or, as we'll see in a second, we kind of will refer to those as inputs. And the range, this is simply the set of outputs. Now you might say that should be set B. Now what set B contains the range, but it might not be all of set B. Now some texts like to kind of do this little circle and show that you're mapping things to it, which is fine, and we might do that when we start talking about one-to-one and on-to later on in the course. But what we're going to look at right now about thinking about functions is I like to think of them, I call them boxes, a function box. So I'm just going to draw a little box here, and this is going to be my function box f. Now this is going to be a rule or like an equation. And what this is going to do is it's going to tell me, what it needs to do to the input. So basically something that comes into a function is my input, and these are my x values. And then this function box, as I said, there's a rule or an equation or something, and that function box then does something to the x value. Maybe multiplies it by 3 and then adds 2. And then what we'd get out of that is an output. And these are, you want to think of these as your y values. Now, we're not necessarily going to always use the value x and y, but that's what you can kind of think of it as far as with a graph. Okay, now before we get into function notation, I'd like to just first talk about determining if a graph of an equation is a function. And there is something that we can do here. I'm just going to draw a couple quick examples, and then we'll write down the rule here. Some of you might be familiar with it already. So I'm not even going to bother bringing up nice graph paper. I'm just going to sketch a y-axis and an x-axis. Okay, so from these here, I'm going to sketch a couple graphs. Now, this first one here that I sketched, this is a function. This second one that I've sketched is not a function. And well, clearly there's something I can tell about this, but let's go back to the definition here. What's the key thing is that each x value gets assigned exactly one y value. Okay, so let's look at these graphs again. Now this is a test that you might be familiar with. It's called the vertical line test. We'll write it down here in a second. But the idea is if I draw a vertical line here, how many points of the graph do I hit? Well, I hit 1. Now, if I draw another vertical line, how many points do I hit? 1. So that means this x value here has been assigned 1 y value. This x value here has been assigned 1 y value. And we can clearly see if I draw any vertical line now on this graph, I'm going to hit at most 1 point. So each x value has been assigned exactly 1 point. So that's what makes this a function, because it fits the definition. Now if I go over here, we can quickly see if I draw just a horizontal line right here, I'm hitting 1, 2 points. That means this x value that I put a tick mark by has 2 y values assigned to it, which breaks the definition. The definition says you can have exactly 1 y value assigned to each x value. So I have 2 y values assigned right there, so that is not okay. And this is formalized in something called the vertical line test. So the vertical line test is the graph of an equation is a function if and only if any vertical line drawn touches at most 1 point on the graph. And you might say, well, wait, doesn't it have to be exactly 1? Well, the reality, though, is you're thinking in this first example, we had a domain of all real numbers because we could plug in any value for x. But we don't always have a domain of all real numbers. And we'll go through an example here of that in a second. I do want to point out something. This vertical line test is what we call a theorem. And this is not true because we say it's true. This is true because we could prove it from definitions. This if and only if seems a little weird here when you first see it. But what that means is you can go both directions. So if you have a function, then you will pass the vertical line test. So that means any vertical line will touch at most 1 point. Then if you have a graph of an equation and any vertical line touches at most 1 point, that means it's a function. So you can go both directions in this. Basically, I could switch the wording in the sentence and it wouldn't change anything. That's why we put the if and only if. If you have just an if, you can't change the order of the wording. So you'll maybe get a little bit more hang of that when we see more theorems later on in the semester. Okay, so let's look at an example here where we apply this at most 1 point. And this is a pretty easy example to look at, so I'm not even going to bother getting a great set of axes here. I'm just going to kind of get a rough sketch of some. And then we're going to do a rough sketch of the square root of x. And so here, here, and then roughly here. And so this is what the square root of x looks like. And of course, the reason it looks like this is even though we know about complex numbers now, we're only going to be talking about in these chapters or these videos currently about real valued solutions, graphs with real values. And so square root of x, I can't put negative numbers in because then I'd get complex or imaginary numbers. So I can only put 0 or positive numbers in. So that just means my domain here is x is greater than or equal to 0. And we'll talk more about domain in the next video. Alright, but what does this mean as far as vertical line test? Well, if I draw a vertical line over here on the left hand side, it doesn't touch any point. That's fine, it's just, that just is basically referring to the fact that this isn't part of your domain of your function or equation here. But then if I draw a vertical line where I have my domain, we can see any vertical line I'm going to touch is going to hit 1 point. So again, that makes this a function. Alright, so enough about looking at graphs of equations to determine if they're functions. Let's wrap this up here, this set of videos, by talking about function notation. Function notation is something, some of you maybe are familiar with this, but if not, you want to become familiar with this. We'll be using this essentially for the rest of the course, and subsequent math classes will use function notation all the time. So remember that function box I had drawn where I had an input and an output. Well, the input to that function box is x. Now it doesn't have to be x, it could also be a different variable, which I'll talk about in a second. The output, now we're not going to say the output is y, I'm going to say that the output is f parenthesis x. And this is actually read as f at x. Now it is a y value, but we're not going to say y equals, we're going to say f at x equals. And then we have an equation, and that equation is that rule that was inside that function box. And as an example here, we could have f at x is equal to, for instance, 2x plus 1. Now, sometimes people like to think of it as, well, remember you have the equation like y equals 2x plus 1, and we just looked at that in some of the previous videos with linear equations, and you say, oh, you're just replacing y with f at x. And that's fine to think about it that way. But we are really going to want to use this function notation. It's actually got a lot of power, especially when we start talking about composite functions and other things of that nature. This notation, function notation, is better than using this y equals 2x plus 1. Now, as I said, it doesn't have to be x and f at x. You could have g at x, h at x, or for instance, you might not even have x. You could, for instance, have a variable t, and then maybe your output is s at t. And then the equation is s at t equals 3t squared plus 5t minus 1. And it doesn't matter that I've used t now. That's just my horizontal variable. S at t is my vertical variable, and then that's my equation. Alright, so the next thing here to wrap up this here is going to be evaluating a function. Now, evaluating a function is very simple. It's really not anything different, it's just notation really is the difference here. We've done evaluating functions plenty of time, we just haven't called it evaluating functions. So evaluating a function. So let's just dive in an example here, and once we go through this example I think you'll see that it really is quite straightforward. So let's look at a function, and we're going to start with f at x is equal to 10 minus 3x squared. And then the directions are going to be to evaluate f at 2, f at negative 4, and then f at x minus 1. Now, when we see f at 2, this is literally meaning substitute 2 in for x and evaluate. So we've clearly done this before. If you had, for instance, instead of f at x, y equals 10 minus 3x squared, we've plugged in values for x to compute y. We're doing the exact same thing here, we're just using slightly different notation. So f at 2 is just simply substituting 2 into this equation and then evaluating. So let's go ahead and see what we have here. F at 2, this would be 10 minus 3 times 2 squared, which now we just evaluate. This would be 10 minus 3 times 4, 10 minus 12, which is negative 2. So we would say f at 2 equals negative 2. Now, just again to kind of put this back onto graphs, because we will be talking about graphs of functions, this would essentially be the point x equals 2, and then the y value would be negative 2. Alright? Alright, so then f at negative 4, really there's nothing too different about this. The only thing different is we're just going to substitute negative 4 in. So we'd have 10 minus 3 times negative 4 squared, which is 10 minus 3 times 16, 10 minus 48, which is negative 38. Now, the last one here, it's not difficult, but it's different than what we've done before, f at x minus 1. Now, this is still the same process, except instead of substituting a number in, we're going to substitute x minus 1 in for x and simplify. Now, one of the very important things here is to make sure when you substitute it in, notice how I put it in parentheses. And that's going to be critical anytime you're doing this kind of substitution, because we have to make sure that we distribute things properly, or in this case with a square, that we square things properly. And so what will we have here? We'd have f at x minus 1 is equal to 10 minus 3 times x minus 1 squared. Now we just obey order of operations. And order of operations will tell us that we should do the x minus 1 squared first. Now you could FOIL that out if you wanted to. I'm going to use the special product where this is equal to a squared plus 2ab plus b squared. I'm sorry, a squared minus 2ab plus b squared. So this would be 3 times x squared minus 2x plus 1. Now I'm just going to emphasize, if you don't see that, just simply do the FOIL of x minus 1 times x minus 1, and you would get x squared minus 2x plus 1. Now, of course, we just still need to simplify this out, so this would be 10 minus 3x squared plus 6x and then minus 3. And then we'd finally simplify, and we'd get negative 3x squared plus 6x. 10 minus 3 is 7. And so we won't get a number for f at x minus 1. We get another equation instead. All right, so that takes us to the end of the first one. We're not done with these functions just yet. We have another video that will talk about functions some more.